Okay, okay, I guess. Uh, First of all, like, I see that like some of you guys are struggling with homework, but I don't know, not many of you are here. I was thinking like, um, I should give some numerical example. I'm not sure I should wait for a couple minutes to get more people, or like I should just start talking about give a little bit more numerical examples. So let's see. Oh, okay. I see at least one more. So okay. Let me do something like this. Let me just give several more numerical examples because I see like several of you are struggling with homework. So and then I after that we'll come back to continue to talk about differential entropy. So let's uh let's consider, okay, let me make up an example. Let's say like we have two dices again, like maybe two dices. I have like two distributions. So dice one, let's say like dice one is distributed like that. So I have like, of course, I do six outcome, right? Um, Maybe I call it dice A here, dice A. Then I have dice 5, 6, and I have dice B here. 1, 2, 3, 4, 5, 6 also. And then like say for dice A is kind of biased for one. Let's say like I say for getting a one with probability is 0.5, and then the rest is a 0.1, let's say. And then for dice B, like I have like of them like 0.1, and then I say except maybe 6. Like in this case, I have a high probability of getting a 6, let's say. And okay, so let's say again trying to do like um MLE map and and also Bayesian estimate. And let's say I have like tossed this dice several times. Like, okay, first of all, like, I need to give some prior here. Let's say dice A with occur with probability like 0.6, like, it's more likely to get a dice A than dice B, let's say. And then let's say I toss the dice. Okay, first of all, we randomly pick the dice, right? Let's say when I pick a dice, then we stick with that dice, and then we toss it like 3 times. Let's say I got like maybe a 1 6, maybe I make up something like 3 times a 6 5 1. Let's say, I don't know. So then maybe 655, 654. I don't know how it will change, right, the number here. Mm, maybe one. Let's see. I'm not sure. Maybe 154. I don't know. Like okay. Let's say like if I pick the dice and then I just randomly pick up a dice and then I toss it 3 times. Of course, I don't know which dice it is. Like whether it's a dice A or dice B. Now then I want to estimate like probability of getting one. uh, for the fourth toss. So what will that be? So this is like, let's say, I guess I do you want to try it out? Like let's this is like um if you can do the homework, I assume that you should be able to do this. Um but so how about I give you like a minute or something? Like it should be uh the setup is relatively simple. Let's see. So is the question clear? Like just like say like start with MLE. I'm not sure the map will have the same solution here. Actually, I didn't. But let's say like just okay. Yeah. So how about the rest of you guys? Are you guys um working on that? Like, do you need more time? So so if we are looking for the maximum likelihood estimate, so first of all, like we should estimate which dice like uh is the dice we pick up, right? So and we just look at like the two dice like getting outcome, like what's the probability of what 5 6 getting 1 5 6 given like dice A, like A, that will be like if it's A then maybe 0.5 like for the one here, like yes. And then like to get one you will have probability 0.5, get five with probability 0.1, get four with probability 0.1, right? So this is like the probability to get dice A. And then like for dice B, like uh, I will have like 0.5, oh sorry, for one it will be 0.1 and 0.1 and 0.1. So apparently like dice A will be have a higher probability. So for MLE estimate, we will first like kind of like guess like which dice we picked up. Then afterward, we will just say, okay, the probability. So we estimate probability that getting one, this is like getting one for the fourth toss will be give given this observation 154 will be just a probability getting a toss given like A, so therefore it's 8.5. So that's so if I'm doing a map instead, so let's see. So I guess I will ask you guys. I didn't. Let's make a different color here. So if I'm doing map, the only difference is I will take the pi into account as well. So therefore, like, the probability of this will be actually, of course, like, this should be proportional instead of like really equal earlier also. So great. So if proportional, but we also need the prior. So prior is like 0.6 and 0.4, right? So I also multiply with the prior, I multiply with 0.6, and here multiply by 0.4. Actually, I didn't make any difference here. Apparently, still like dice is bigger. It's not really a very interesting example here. So therefore, like in this case, even I use map, I will get the same estimate. Oops. we'll get the same estimate. It's like 0.5 again. So hopefully it's clear. So um, because in this case, the probability getting 1 for 4, like 1, 4, 5, I will try to see like which one has a higher posterior probability. One is equal to this one is or I should say one is proportional to this one is proportional to this one. So A, for the case A is bigger, so therefore I will approximate this one with the, as I dice is A, and then I will approximate 0.5 as well. So now let's do the Bayesian one, maybe Bayesian. So I will just give it as a question again. I'll say, okay, for Bayesian, like what would be the probability? Again, the probability of getting 1 for the fourth toss here. Let's see. Yeah, it seems low. I didn't compute it yet. It seems a bit low. Uh, I would guess a bit higher. Most likely, I think it should be bigger than 1/6. Yeah, because you see, like you fold this dice, let me see before you look at the number. Like sometimes it's good to see if you can get some intuition and then guess a value, the range of the value. Then you can check your numerical value. Right? I would say that number should be larger than 1/6. My rationale is like that if like the dice are independent, okay, in the sense like if both dice are unbiased, then if I toss it several times, of course like this I get 1/6, right? The fourth time the estimate should be 1/6. But now because I have the dice, I know they are biased. Okay, yeah. So because like the dice is biased, then actually you know that like from the observation here, it's more likely that like the dice you picked are actually dice A, right? So because the dice you picked is more likely to be dice A, the probability of getting one like should be larger than an unbiased dice. So you guys are computing. So maybe I walk a couple steps here and then let you guys continue. So for Bayesian, like of course I should be let's say if I want to do like what's the fourth toss is like one. Let me just shorthand like this. Like fourth toss is one, given that the earlier toss is 154. Right? So this will be kind of like equal to two different cases. So maybe I don't even need a summation. Maybe just write it explicitly. The probability that like 154 and the actual dice is A, and then I plus P1154, the dice is B, and then this is like equal to, I can like expand that, like this will be, oh sorry, like oh, there's a typo. Yeah, sorry, it shouldn't be here. Okay, let me rewrite it. 1A154 plus P1 B154. So in the sense like this is like probability the fourth toss is one, and also like this is like the actual dice is A, and then this is a probability actual dice is B. So I'm just marginalizing this variable, right? If I add this together, we'll just get here because I marginalize that this variable disappear. So then this I can um, I can expand that way. This is a P A given 154 and then P 154 A, something like that. But given the dice is A, the early observation is not important, right? So actually this is gone. Like it's like conditional independent. Given the actual dice, like it's the previous observation is it doesn't matter anymore, right? Plus like P B 154 P1 given B here. And of course, I know what's P1 given A here is this one is a P1 given A is 0.5, right? And this is a 0.1 here. And then of course you just need to compute this here. And this more or less you can compute this from here, right? So this is for Bayesian. You guys are working on that? Like, do you have a question like up to here, let's say? Maybe I don't know. Yeah, but it seems reasonable. From for probably sound reasonable. Let's see. We have from here like this. I know it's proportional to this and proportional to this, right? So I can write P one. Actually, sorry, like actually, yeah. Here like there's a mistake also here. I'm sorry about that. I should really say the posterior is proportional to. When I say MLE, actually, this when I first write it, it's actually called. Actually, like I was not wrong earlier. Also, like A B here because it's for MLE. For map here, I should write the posterior instead. I should say like P A given 154 is proportional to that, and P B given 154 is proportional to that. So I can say like P 0.0154 is equal to like 0.5, 0.1, 0.1, 0.6, or times some constant k, it doesn't matter. And point PB 154 is equal to 0.1, 0.1, 0.1, 0.4 times some k, right? So, but what is k? Like if I add this together, right, this will be sum up to 1, right? So therefore k should be just equal to 1 over, okay, maybe I go a little bit fast for this one. I hope you guys can see it, right? So this is equal to this one, and this is equal to this one. Now if I add these two together, right? So if I add these two together, I will get 1 here on the left hand side, and for the right hand side will be equal to k. So I have 1 equal to k times 0 0.5, 0 0.1, 0 0.1, 0 0.6 plus 0 0.1, 0 0.1, 0 0.1, 0 0.4, right? So therefore k is just 1 over this guy here. It's actually it's definitely like what we expected. Like essentially what we mean is like this guy is just equal to 0.5, 0.1, 0.1, 0.6 over this thing here. So I assume you guys are correct. Like let's see. Like maybe I should still like check it myself. To pull out an octave of MATLAB. Let's see, or like so I have like PA. I'm fine. Yeah, that's great. Okay, so 0.0034. Okay, that one is 0. So I got like PA this one. Got this one is a pawn. AA235, something like, I'm not sure, like hopefully I didn't have any typo here. And of course, like the other one will be just like pawn 11765, right? So then like if I AA wait a sec, I get something like not the same as you guys. I don't know. Like, do you get the same PA and PB like as I see? So okay, I guess maybe I should no, it can be myself also. Like if you two, let's see, 0.5, 0.5, 0.1, 0.1, 0.6. Okay, I have a mistake here. Apparently, I guess is that 0.5, 0.1, 0.1, 0.5, no, it's like 0.5, 0.1, 0.1, 0.6, 0.1, 0.1, 0.1, 0.4. It seems right. 0.1, 0.1, 0.1, 0.4, 0.5, 0.1, 0.1, 0.6. Yeah, okay. That's good. Yeah, yeah. So if I have that like, oh yeah, maybe you didn't normalize it. That you need to be careful, like because this is not are actually equal to this one. It's just like it's proportional to this one. So it's like times some constant here. So then you need to find the for you to do Bayesian, you need to actually find the posterior probability. That's actually one reason that later on you see that like why Bayesian is can be in some cases like difficult to find because you need to find this normalization factor like this one here, the k here. And if you have many cases, for example, if this one is a continuous random variable, then this become an integral, and maybe this integral is not integrate, it's not cannot be, it's not integrable. So that I'm not sure that's the word. So then you basically you cannot correctly estimate this posterior probability, then you cannot use Bayesian. So yeah, but I think in this case I say something like 0.4. Yeah, it should be, yeah, it should be something like that. So okay. Uh yeah, make sure you understand this because I can quite assure you that like this is very easy to ask like as an exam setting. So of course it won't be exactly the same, but like you expect like similar question probably occur in the midterm and so on. And okay, let's use the similar example here. But again, I have the dice here. Dice, I toss it, right? I have the dice again. And I have the dice. Now, like, let's say like in previous case, we can do get this precise value, like in the sense we know precisely what kind of dice we had, right? So we don't know which dice to pick, but at least we know there's a dice A, dice B, and we know precisely the probability for getting a 1, 2, 3, 4, 5, 6 is precisely what number for that particular dice. And it's not, in most cases, it's not very reasonable like that. We can model that. So therefore, like a better model will be um, just using a prior um, kind of directly on the probability of the each of the outcome. So, and of course, we can make a different prior. As I mentioned, like the reasonable prior will be the original prior. I quickly go through that, quickly went through that. Because it's the conjugate prior. Think of like, for example, again, like if I toss like 145 is the 145 I forgot earlier. Uh, yeah, I have like a memory of the goldfish, basically 154. Okay, anyway, yeah. So if I toss like something like with probability 154, so think of like the probability of getting a 1, 2, 3, 4, 5, 6 is just like P1, P2, P3, P4, P5, P6, right? So then to get precisely this outcome, like 1 and then get 5 and then get 4, the probability of getting that will be just like P1 times P5 times P4, right? Something like that. Now, if you have a long sequence of that, like for example, if you have like toss it, okay, okay. So anyway, so there's a n tosses here. Let's say I have n tosses here. I have n1, p1, n2, p2, n3, p3, and so on. Let's say I toss it n times, say n can be 100, and then I have like n1 time to get 1, n2 times to get 2, and so on. So therefore, like it should n1 plus n2 plus n3 plus n4 plus n5 and 6 should sum up to big N here. Now then, given this p here, the probability of getting this particular um, number of tosses will be proportional to p1 to the power n1, p2 to the power n2, p3 to the n3, p4 to the n4, p5 to the n5, p6 to the n6. Well, actually, like, yeah, I say proportional because if I don't say exactly the order of that, like that can be like a combination of that, right? But that combination will be okay. Precisely should be something like that. Should be like uh the probability of getting like m1 n6 given p1 p6 m1 n6 meaning that I get like n1 toss n1 of 1 and n2 of 2 and n3 and 3 and so on. We will proportional to that, like, or like more precisely actually equal to this one, and that will be like how many combination of that, like it'll be like, let's see, uh yeah. Okay, make sure I'm correct. So like this is like something like that, I think, like n1 factorial, n2 factorial, n3 factorial. Don't worry about this one because this is just the number of combination here. And note that like this one does not depend on p here, right? And if I want to optimize p here, then this number, I mean, this scaling factor doesn't affect it. So I mean, I don't actually need to worry about this part. I know it's proportional to this, it's okay, right? And then I previously say like what will be the Dirichlet prior? Maybe will be like or like the Dirichlet distribution will be something like this, like alpha 1 minus 1, p2 alpha 2 minus 2, sorry, not 2, alpha 2 minus 1. So on p6 alpha 6 minus 1. So this is the Dirichlet. Of course, like, there will be like some scaling factor here also, like, but it doesn't matter. So in the sense that because this will be a distribution, so this should be normalized to 1. So I mean, let me maybe just write it like this. This just big K here is just scaling factor. So this is like Dirichlet function P1, P2, P6 given alpha 1, alpha 6. It's very similar to beta, right? But you see, like I now it's the difference is like I don't have just two outcomes. I have like more than two outcomes. So and as you just did the homework there, uh, know that like if you have a Dirichlet pi, if I have a Dirichlet pi with like parameter alpha 1 up to alpha 6 here, you see if I multiply this observation here, what will happen is like I have something will be proportional to p1 n1 plus alpha 1 minus 1, right? And p2 n2 plus alpha 2 minus 1, p3 n3 plus alpha 1 alpha 3 minus 1, and so on and so forth, right? So, okay, just must ask you a very obvious question here if you are following. So what is this Dirichlet distribution? This apparently like this is like some multiplied by some scaling factor as well. This will be a Dirichlet distribution, and this will be a Dirichlet distribution for parameter for variable p1, p2, and so on, p6. What will be the parameters here? Let's say I write beta 1, beta 2, up to beta 6 here. So what will be beta 1 and so on, beta 2? So what will be beta 1, let's say? What's beta 1? Yes, right. It's very simple. Right? It's just M1 plus alpha one. Right? So it's very similar to the homework. Right? Actually, this is a little bit more. Um, I shouldn't say just very little, tiny more complicated than the homework because in the homework you only have like two. Um, actually, for beta, like you really just have one parameter. Is that like two? Like so here, yeah, you have two. Yeah, you have two. So here, like you have like six parameters here, right? But it's still like it's more or less just like um your basically if you have a prior, it's like this one, and then you have an observation like getting like m1 outcome for one and m2 outcome for two, or sorry, m1 of one, m2 of two, and so on. Then you will just have like the new parameter will be um, m1 plus alpha one, yeah, and beta two, and two plus alpha two, and so on and so forth. Okay, now I guess we can do some numerical example here. So I can ask you the same thing. What's the probability of getting the fourth toss is one? Fourth toss is one. Uh, let me make it okay. Let's say like alpha one. So let's say the initial prior is like two, 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 something like that. So let's say the earlier one is like the what I mean is like let me maybe okay this I try to okay let's start a first page here. So again 15154 let's say the prior is Dirichlet P1 P6 and 22222 let's say all are two here, and then my observation is 154 right, and then the question is like probability of getting one for fourth toss. So again, I can ask you MLE map and ML actually Bayesian as well. So I will give you some equation here for 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 Dirichlet distribution. The mole will be at alpha mole for occur at mole at alpha I minus one. Let's see, alpha 1 plus alpha 2 up to alpha 6 minus 6. So if n is 6, then it will be like this. So okay, my n here say um, the number of outcomes here. Yeah, number of outcomes here. And the average mean is at alpha I over alpha 1 plus alpha 2 up to alpha 6. So for example, I give you an example here. If my parameter is actually 1, 1, 1, 1, 1, I will have like a uniform prior because I remember how the Dirichlet looks like. When all of these are 1, then this piece will be gone. Right? So it will be essentially like the distribution will be like just a constant. So therefore it's uniform. And also like in that case, you expect the mean will be just 1 6, right? So and you can verify that, right? So the mean will be is all 1 here. Then mean will be like 1 over 6, 1 over 6, 1 over 6, and so on. So what I mean is like for each of the. So okay, here may be a little bit confusing. So I have like mean for like 6 outcomes here, because what I mean by the mean is the mean probability of each of the outcome. So for example, like the mean probability of getting a 1 will be alpha 1 over alpha 1 plus alpha 2 up to alpha 6 here. So if alpha of the alpha is equal to 1, then it will be just 1 6. And this is uniform as we expected. On the other hand, the mode is a bit tricky. I don't think we can use this formula here for, it's just like the beta case here. When your alphas are bigger than 1, then your mode will be just given by this formula here. But if it's not the case, you probably need to plot it out. It probably will be a bit more complicated. So therefore, I pick a bigger alpha here. So just avoid this complexity complication here. Actually, if your alphas are all 1 here, your mode is not defined in this case, because actually everything is uniform. For 2, no. 2, you don't have wait a sec. Is that the same? Maybe, let's see. Yeah, I think so. Yeah, in that case, it will be the same actually. If your parameters are 2 here. But note that I have oscillation here as well. So note that like you need to take into account the oscillation now. So is that clear? Maybe we start with the map. I guess the map is the least, or like even the Bayesian is actually map and Bayesian in this case is the same. Only like one will be like using the mode, one is using the mean, right, for the estimate. How about we start with the map here? Like, can anyone answer that? Like, with this setup here, if I want to get what is the probability of getting 1 for the 4th toss? So for map estimate, like what will be the probability? So the intuition, like it should be probably bigger than 1 as well, right? Oh, sorry, bigger than 1 6 as well, because I observed some 1 earlier. It seems like it's more likely to get another 1. So I know like, oh, okay, it's getting back to this one here. This is the observation, right? This is, and this is your prior, right? So to absorb the observation like into your model, this is like simply what you did, right? So the posterior will be essentially the same form as still a Dirichlet distribution, but the parameter will change. This is how it changed, right? The original parameter of the prior is just alpha 1, alpha 2, and so on. Now, if you observe like m1 so many 1, then you need to update the alpha 1 by m1 plus alpha 1, right? So in this case, well, so what happened? Like I observed like 154. It means like how many 1 do I see? Yes. So and similarly, you okay, you will see like the posterior. So for these two case, okay, I guess I'll let you try out. For these two case, we will take advantage of the prior, right? Or at least the prior given by the question. Like someone give you the pi, you are going to use the pi for map and posterior. So for map and Bayesian, for both cases, the first step is try to find the posterior, right? And the posterior, like in this case, if we are playing with like the Dirichlet pi or like the conjugate pi, that's why people love conjugate pi. You see, it's so simple. Essentially, it's like after taking into account the observation, we still have a Dirichlet distribution. Only the parameter change a little bit, right? So then the new distribution is still a Dirichlet. I mean, the posterior is still a Dirichlet. P1, P2, P6. Now the parameter will be like, I see 1, 1 here, right? So therefore I have 2, I should add 1, right? And how many 2 do I see? I did not see any 2, right? So therefore, like, I still should have 2 here. And I do not see any 3 here. I have 2 here. And I see 1, 4 here. So I have like 3 here, right? And then I see 1, 5 here, 3 here, and 6 here. So the posterior should have distribution like this, right? So then what was the map? Like, okay, it should be very obvious now. So what would be a map estimate for probability of getting 1? Yeah, right. So uh let's see. Yeah, I think you're right. Yeah. So 2/9. And this is good. I think it should be one. That's a sanity check. I think it should be bigger than 1/6. Yeah, as I mentioned, like because I know that's okay. I have one. Okay, I almost give no prior on that, but that's one thing. Like um. Oh, okay. Actually, before I continue, maybe I asked you guys like, to finish all this first, and then we can look at this number, and I think it's something interesting also. So, Bayesian, what is Bayesian? Like, so what will be Bayesian? The Bayesian estimate? Yes, I think. It's like, yeah, I think so, right? Bayesian estimate would be just 3 over sum of all these. So it's like 9 plus 6, I think. So it's like 1 over 3 plus 2, so 1 over 5. So how about MLE? Okay, this may be a little bit tricky. So I'm not going to use any prior here. So what do I mean I'm not using any prior here? No, almost, but you need to be. Uh, Actually, I kind of mentioned that, but maybe I didn't emphasize that enough. W- When 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 I don't have a prior, what does it mean? Um, it means that like I have no information. So then yes, it should be uniform, right? So okay, I'm not sure for the unbiased case. I need to think a little bit. Uh, Let's get the results and then we can come back to that. But it should be uniform. Um, so what parameters will give you uniform? So what is the parameter that you I can get a uniform distribution as I mentioned earlier for the even for the Dirichlet. Which one? Which sets of parameter will give me a uniform um give me a Dirichlet distribution is essentially just a uniform or essentially just a constant. Yes. So for this one, like MLE, like essentially, it just means that I should set the pile to be all ones, right? So that one, that would be correspond to the case that I have no information because like everything is a constant. I have no idea whatsoever at all, right? So if I set it to all one, so you can repeat the step. So it's very similar to the map case, right? The only difference is like now I have the pi is all one. So what will be the value now? What should be the probability of getting one? Do you get a? It should be very simple. Yeah. Okay. Yeah. Probably. I don't know. So you have all ones here now. First, and then you make an observation like that after taking into account the observations. So it should become a Dirichlet of like parameter um 2 1 1 2 2 1 way, something like that. So then the probability of getting a one uh, if using MLE, I am going to estimate using the mode, right? So in this case, I can still use this formula. So if I have like alphas are less than one, then I will have trouble. But like all of that is bigger than equal to one, so I'm okay using this formula. So wait a sec. Actually, I guess I made a mistake here. Two one. Oh yeah. Right. Why am I waiting? Oh yeah. This okay. This is not one. Is a stroke here. So then the probability should be 2 minus 1 over 2 plus 1 plus 1 plus 2 plus 2 plus 1 minus 6, something like. So that should be one third. So the probability is one third here. Okay, now get to the case that whether we assume anything is unbiased. I think it's not because you see, if I really assume the cons to be unbiased, or no, not con, I have a dice here. If I assume the dice is unbiased, I make the observation. It doesn't change my um my belief that the dice is unbiased, right? So for the fourth toss, I should still get the probability of getting a one should be just 1/6, right? So for all of this, like we I would say like thinking stuff is unbiased pretty live. Or like we ignore the observation there, right? Now we have more observation. Of course, like if we keep on believing this unbiased, then we just essentially discard the information we had, discuss the observation we had. So and uh and for this case, you see like each of this is bigger than 1/6 is a kind of a illustration that like we are not really believing the dice to be unbiased. Okay. Anyway, so okay, I guess I what I'm going to do next is a uh, some still using this as a example, but let's say let me use the first setup as an example to compute some entropy values. So let's say I'm not going to use compute MLE and so on and so forth anymore. But let's say again, I have a dice A, dice B, like something like that. Go back to the original setup here. And okay, let's say let's denote some introduce some notation here. So let's D be the dice. So the random variable is the dice random variable that specify which dice you pick. So it can be dice A or dice B. The outcome can be A or B, right? And B. And the probability, as mentioned earlier, is like getting A will be 0.6, getting a dice B will be 0.4. And then I have the probability of getting this outcome. Let's use O as the outcome. Random variable is the outcome. Now, given this setup here, can you try to compute HO? This is another question here. Sure. I mean, I have like the same setup as the original, have two dices, and then you pick up the dice, right? So let's say you pick up the dice and take this action as a random variable, right? The dice just denote the random variable by D here. So D can have an outcome A or B, something like. And then you toss the dice and you get an outcome, right? And we denote the outcome as O here. So let's say just consider this outcome here, like for this setup here. Of course, I can have O1, O2, and so on. Like O3, O4, like will be like the outcome for the first toss, outcome second toss, and so on and so forth. But essentially they are ideal, right? In the sense like I mean the problem doesn't change over time. So in general, you have like HO1 is just equal to HO2 and so on and so forth. But here, so therefore I just write HO here. So here I'm asking that what will be the entropy of O here. This is similar to your homework assignment there, like the second homework, but with some actually the second homework there, like referring back to the first homework, like we have the weather and the temperature there. So we have the weather keep changing every day. So the setup here is like a little bit easier because once you pick the dice, it doesn't change. So you have the same dice, kind of using the same dice like continuously, like afterward. Um, And O, of course, O of the outcome, like 1, 2, 3, 4, 5, 6, right? No, okay. Um, you know what's HO in general? For example, you have a random variable X. Look at the distribution is PX here, something like, we say this one is like PXX or simply PX here. HX is expectation minus log PX, right? Or like sum over PX log PX, right? So to compute the entropy, you need to first find the distribution. Once you know the distribution, you can just compute the entropy as the. So Trey have an answer. So that's let's see. Okay, that probably is incorrect because I remember like it shouldn't be bigger than the number of log the number of outcome here. For example, like you think of like I think of like what's HO. HO is will be like how many bits on average are needed to store that information, right? It cannot be more than 3 bits in this case because I only have 6 outcomes. I can be pretty dumb, just label like just kind of code this into 3 bits, right? Yeah. This looks right, so I need to check the macro later. Yeah, okay. So if two of you get the same number, more likely it will be correct. So, but I will wait a sec. Like maybe Sarah is trying that also. Um, by the way, for you guys, if you can, yeah, if you already finished with HO, maybe you can compute HO given D as well. So, but don't give out the answer yet. Like you can wait for the others, but like meanwhile, you can try to compute this as well. Yeah, actually, if you're in front of your computer, like it's easier to use computer instead of using a calculator. Yeah. Yeah. I usually just use Octave or like MATLAB or like even Python, NumPy. Yeah, it'd be easier. It's okay. Yeah. Mm, yeah, I'm not sure you're using a calculator. Like that's yeah. Okay. Yeah, I'm thinking whether I want to show my screen. Uh, the problem is uh once I show the screen, the whiteboard will be all erased. mm. So okay, for Trey and Michael, are you done with the conditional entropy? Like, are you getting there? I guess you can. Yeah, it's okay. You show the answer. Like, let's see if I what numerical value do you get? Let's see. Yeah, probably right. I guess. Uh, yeah. So, okay, for you guys, quick on these things. Let's see. You may also try let's say I01, O2. Are you still working on that? Like, I guess yes, you need to find the O P, yeah, the marginal distribution of O first. Yeah. Okay, if I'm going to show my screen, I guess I better copy the question first because um, it'll be gone and, on my computer as well. So I have like this dice A. Oops, it's not. Yes, that's correct. Yes. Just it's okay. Let me see if I can. Okay, now I can write it, I guess. Okay, let me copy the sub at least. So, but anyway, like let me let's come back like 4:30. So if you can work on the others also, like I mean work on like this also like HO given D and IO1, the mutual information between O1 and O2, basically the outcome of the first toss and the outcome of the second toss, and see like what we get. Yeah. So okay, I let's come back in 15 minutes. Yeah. Yes. And okay. I guess like let me just show my maybe my work here. So we have this problem. We say we have two dices again, right? A and B. So we randomly pick one of them, and then like dice A is biased like with one is more likely, and dice B is biased toward like six with like half of the chance to get a six. And then we have like zero point 0.6 probability to get a dice A, 0.4 probability to get a dice B. So now to find like HO, we need to find the marginal distribution of OA. So I set like PA here. It's just a probability of PA. So of dice A is say 0.5, 0.1, 0.1, so on, so on, and so on. Dice B is I say call it PB here. Right? So then over P can be like PA times 0.6 and PB times 0.4. Right? So then if I compute the entropy, it's like minus naught, okay, P times minus log 2P or something like that. I have a minus sign here, say, and then sum of this. So it says 2.3 something. So how about HO given D? Like can any of you are around and try to answer that? Like what would be HO given D? Yeah, if you're in front of the computer, like use the computer is way faster than like using a calculator. Uh and by the way, like our midterm will be take home. So on account, like because this is an online class, right? There's no way like you, yeah. So and but they say again, I will be take home for several hours, something like. So you can use any tools. So I will make sure you cannot Google the answer though, like so. But you can just use MATLAB Octave. It'll be faster than using a calculator. So I think Trey computed that earlier, but I think I forgot. Yeah. So anyone else have got the value? Like anyone else got the same value there? Okay. And a sanity check, like make sure that you have like conditioning like reduces entropy. So if you are conditioned on something, think of again like what's entropy mean is like the amount of or number of bits required to store that kind of information, right? If you have some additional information regarding O here, definitely like you will list less number of bits. So therefore this should be bigger than equal to HO. HO should be bigger than HO given D here. So it can be equal, but cannot be the other way around. You cannot have like HO given D bigger than HO. Mm. Anyone else are computing that? Like so, uh, maybe I can help you a little bit here. Like this one is actually weigh the sum of the conditional entropy for each of the cases, right? So be HO given small a. That's when like condition and A then have with some distribution, right? Then you can compute with that distribution. It was HO given small a, and then also like HO given small b here, and HO given D here will be just weigh the sum of these two by the probability of getting an A and probability of getting a B. Right? Okay, yeah, I think like you are not, okay, make sure you know like what this here, HO given A here, um, if I call this PA here, should be just, um, okay, I mean like, the West are trying as well, like before trade, beside trade. So yeah, I don't know if you guys are actually around. So anyway, like maybe I will just say for the time being, for the, I mean, what should I say? Like because of the time, I guess I will just give out the answer here. So so I guess if I say PA is the probability distribution given A, then I can find like HO given A will be just like that, right? Sum minus PA dot log 2 PA, right? So this will be like, if I getting an A, if I A, HO given A will be just this guy here. And it's the weighted sum, like let me times P. Probability of A will be just 0.6, right? Times 0.6 plus similarly PB dot 2 PB, and probability of B will be 0.4. So okay, I get, oh actually this is 2. Oh, this is like so miracle. Oh. um okay, anyway, this is just a coincidence, I guess. So yeah, that give 2.16 here. And yes. And let's see. I don't know anyone of tried this here. I just look at this and I realize this is actually not too easy to compute. At least it has quite some step. Maybe we try something simpler first. IOD, what is that? Very simple, right? What's IOD here? So okay, I guess I probably you don't remember those equation and formulas and so on. So, but I guess that's reasonable. So I'm jumping ahead, but like this may be a good memorizing tools here. If I have like random variable x, y, and z here, I can draw some Venn diagram here. Is x, y. Let's say, let me draw more x, y. Let's see, this is just x and y. Let's say, and basically, if I think of like this circle here as hx, then this part here will be h x given y, and this part here is ixy, and this part here is a h y given x. So so therefore, like you can see, like basically hx here is equal to hx given y plus this area is ixy. For two variables, it's okay. Actually, I can even do three variables, something like. So okay, maybe I pause here for a say. So knowing that, so what is IOD then? Like this should be very simple, right? Since you already compute HO and HOD, HO given D. Yes, it'll be just the difference, right? So it's like just 0.2. Now for this diagram, because I already like opened the Pandora box, I guess I need to continue to say more about this diagram. So there's some caveat for this diagram here. Let's see, can I just Control C back? Let's see. So say I have like X, Y. I can add even one more variable, like let's say X, Y, and then this Z here. Now, then each of these pieces have some meaning here. For example, like this piece here will be I, X, Y given C. Oh yeah, this is a IOMD. Yeah. Notation is there's a semicolon here. Yeah, it's not a comma. It's a semicolon and not a stroke. Um yeah. Sometimes like people, okay, you see people use comma. That's actually is I should say like if it's not incorrect, it's bad notation because it's of course you can understand this is IXY, right? You know, okay, only two variables here, but you can say something like that, right? IXY and then Z, right? So then if you mix up like semicolon and like comma, then like there's some confusion. Like what do you mean by that? So but that indeed like in the literature, sometimes you see people like being sloppy and just use like comma, but most of the time people are very careful. Um, I'm actually when they do that, if you're the reviewer, you can just point out, oh, this guy is sloppy. You shouldn't write like this. I'm sure that you know something actually, basically. So okay, let's get back to here. Like this is a ISY given Z, and for example, like let's say this part here, this region here. Can you guess actually? By the way, can you guess what is this? Just give some guess. Like I don't know. Not quite right. So this region will be HY. The whole circle will be HY. But if just this green part here won't be HY. So remember, like for example, like earlier, we have say this part here is H given Y. So you can guess now this would be something like most likely HY given something, right? Yeah, given XMC. Yeah. Actually, this file is HY given XMC. So I say this is like Pandora box. It's very nice. It seems like you, oh, okay, I understand lots of stuff now. I can make addition and here and there. But the problem here is like the part right in the middle here is usually not defined. Like at least most author won't define that. I found one textbook though, like called this IXYC, but like definitely not something, what should I say, very commonly defined. Most textbook won't do that. For a very good reason is like for all these other region here, they are if this random variable like so here okay if we are considering discrete random variable for all the other parts here they are non-negative. So like you look at like IHY given XZ, IXY, and so on. I didn't show that, but okay, it's obvious that like entropy and conditional entropy are non-zero. I haven't showed that like mutual information has to be non-zero, but I will go into that like very quickly, very soon. But all these pieces is non-zero. But this part, like you don't know, it can be positive or negative. And so therefore, like a very common beginner mistake is like once they draw this Venn diagram, they will argue something like IXY is bigger than equal to IXY given Z. Because you just read that, like, so this part is IXY, right? So, okay, IXY given Z is this part. Apparently, IXY is bigger than equal to IXY given Z. But remember that because the part in the middle here doesn't necessary to be positive. So if this part is negative, then I can have like the other way around, right? So, and actually we had example for that already, like in the past, because I also didn't elaborate a lot there yet for the mutual information, but actually you can even guess already. When I have like IXY equal to 0, what does that mean? It means that X and Y will be independent, right? That is think of like the physical meaning of mutual information is like how much information shared by random variable X and Y, right? So if like there's no information shared between X and Y, then X and Y will be independent, right? And similarly, this is the case that if this is equal to 0, then it means that like X and Y will be conditionally independent given Z. So if this condition is satisfied, it means that like whenever X and Y are independent, then X and Y will be independent with any random variables Z as well. But we already showed that this is not true, right at the beginning, that when we give a review of probability, that like we gave some example, like these two are kind of independent, these two conditions. So you can have like variables X and Y independent, but X and Y are not conditionally independent given Z, and vice versa as well. So okay, so this is a great memorizing tools here, but again, like be very, very careful for this part here. This part does not necessary to be positive. So don't make this beginner mistake like using this diagram to argue something like that. Like you will get something totally wrong. So okay, maybe try to do this one, but I would say it's a bit more painful to maybe we can do it together. I don't know. So it is a bit more. At least I don't see like how I can do it quickly, like just at this moment. It seems like I need to do it slowly for this. So for I01, O2, let's see what we can do. Like for example, I01, O2 is equal to HO1 minus HO1 given O2, or like HO2 minus HO2 given O1. So we can try to work on this direction. So if I try to compute that, I can try to compute this, for example, like, but it looks quite painful. I know this is a, for example, like HO2 given O1 can be maybe a small o here, and then probability of O, and then so on for that, right? And yeah, it can be quite complicated, especially like PO should be the, yeah, it would be like quite complicated, it looks like. See if we can do some other way. So know that like if we consider this Venn diagram again, so I have like HX, HY here, or maybe I use different color here. Let's say this is hx, right? Hx, and then like this is hy, and then like okay, this is hx given y, sorry, hy given x, so on. And then you see like what I should have hy given x plus hx given y plus I xy will be like this. Let's see. Or maybe easier to see that like, okay, actually I forgot to mention one thing more also, like what is hxy? Different color again. What's hxy? Hxy will be hx plus hy given xy. This is your chain rule. So hxy, the total information for both variables would be like what's the information for x, and then like given that we know x was the information of y, right? So this we kind of like talk about that earlier. And let's see, hx is this one, right? Hx is this one. It's this circle on the right here, right? On the left here, circle on the left. Hy given x is just I show here. This is hy given x, right? So therefore, like hxy is actually the entire area, right? And cause the union of these two circles, right? Okay, the union of these two circles, maybe I use orange here. Actually, maybe hxy. So therefore, should be just this union, right? Union of these two circles is hxy, right? So then then you see that like this is hxy. Then if I have hx plus hy, I will have like this piece additional, right? Compared with hxy. So therefore, like I should have something like hx plus hy is equal to hxy plus ixy. Yeah, actually, of course, I can show it like algebraically also, like because like for example, like this is hx plus hy given x, right? So then this I got cancelled here. Hy, of course, is like hy given x plus ixy. So yeah, in this is true. So therefore, like another way to find the mutual information is that like, I can also write this as like O1 plus HO2 minus HO1 O2. So I think this probably will be a bit easier. I can't promise that also, but I guess I will try to take this direction if I try to compute this. At least HO and HO1, HO2 seems to be symmetrical. Okay, should be the same. So it's kind of like ID here, like you will have the same marginal distribution for all, like over time. And HO1, O2, of course, I can write like HO1 plus HO2 given O1. So, but then I will force to compute this again, then it's a bit painful. Then maybe I should try to compute this like in another way. Let's see. Let's see if I can compute the distribution directly. PO1, O1, O2 is equal to PO2 I have two dice here, right? PO2 O1A plus P2 O1 B here, something like that. So just introduce a dummy variable A and B here. So basically they introduce the D here. That's which dice I pick, and then I marginalize that. And then let's see, I can write this as just a O2 given A. Let's do A given O1, let's say P, wait. PA, P O1 given A, PO2 given A. Oh, actually, do I need to? Yeah, it's okay. Actually, not too bad. So anyway, and PO1 given B, PO2 given B. So it's actually, I already split it. Maybe I shouldn't jump step here. So I have like basically this here. I just use base rule is equal to PA, right? Times PO1, O2 given A, right? But given A, this observation are conditionally independent. So I have like PO1 given A times PO2 given A, something like that. It's still a bit complicated, but it doesn't seem to be too bad to compute the uh not too bad. It's probably still need to use a computer to do that. So then I probably need to for loop to compute the entire O first. Then I have so for each of the O I have 6 outcomes here, right? So I have like 36 combination here, right? For each of this combination of O1 and O2. Um then uh maybe just like to show like what I have, like let's say I just uh try to compare several terms here, just illustrate my point here. So I can consider like okay, O1, O2 have different combination, right? 1 1, 1 2, 1 3, 1 4, and so on, right? So 1 2, what's the probability? PO1, O2. So both are 1 here. So then PO1, sorry, this is 0.5. Okay, this one is 0.5. Okay. O1, O2, both are 1 here. Then this one is like 0.5, 0.5, right? So I have like A is 0.6, PA is 0.6, 0.6. Let me find a pen here. A is 0.6 times 0.5 times 0.5 plus PB is a 0.4. This one is 0.1 times 0.1, something like that. Then I can fill in order as, like, for example, like, okay, maybe I just ask you, what's P 1 2 here? There's a question for that. Was P1 2 here? Okay, maybe you don't see the PA is 0.6 again, PB is a 0.4, and for A, I have maybe need to move this down here so that you can see it more. See it. So I can erase this. So what's this? Oh yeah, I can do that. Yeah. Oops. So what was probability of like getting first just the marginal? Yeah. Uh, 1, 2, wait. Yes, right. So I have so I should get a so probability of A is 0.6. Then for A to get 1 here will be 0.5, right? So 0.5 here. And then like for O2 to get a 2 here, so it'll be 0.1, right? And then this one is a 0.4. For B, getting 1 and 2 is both 0.1, so 0.1, 0.1, something like that. Yeah. So okay, you see my point here. Like I if you need to compute that, like you need to compute this table here. Of course, like you shouldn't compute numerical. I mean, like using a calculator, you should just write a small program to do that. So then like get all of them, and then like you can compute HO1, HO2 with the distribution. So eventually you get a distribution with 36 outcomes there. So you get a vector with like 36 values here. So then you can just like, again, I log, let's say call this P here, it will be log to P. If I use MATLAB notation, it will be a P dot star log to P and then sum over that. Put a minus sign here. So something like this. And this will give you HO1, O2, and then like you can find IO1, O2. And 0.5 because this the first one is I have okay, I expand a PO1, O2 as a PA times PO1 given A, PO2 given A, and so on, right? So if you don't have any problem with this step, so this is just PA is 8.6, right? And according to the probability given by from the problem, then to get a 1, like knowing the dice is A, then like it's 8.5, right? The first toss is 1, okay, probability is 0.5. The second toss is still 1, like the probability is still 0.5, right? And here, if the dice is B, then like the probability is 0.4, and getting 1 is a 0.1 here for the first toss, and then like 0.1 here again like for the second toss. Yes. So okay. So I'm not going to compute the finish the numerical answer for this one. It will take a little bit time, but yeah. So but it can be it's computable. Maybe just quickly ask you like what will be like I01 O2 given D, let's say. It's a question here. I01 O2 given D here. Oh, wait, your that one is not correct actually. Given D here, um, this one is should be HO2 given D minus HO1 given uh O2D something like. Oh, okay, yeah. Actually, I'm not well awake also. Like I have a typo here also myself. O2 O1 D. Of course, you can have O1 O2 swap as well, so it's symmetric. Or it can be equal to let me erase that. Or it can be equal to O1 given D plus HO2 given D minus HO1 O2 given D. Okay, I won't. I guess honestly, I shouldn't let you to compare it like because if you just compare it like it will be quite elaborate try to compare it. But the point is that you should be able to see that like for this one here, you have some conditional independence here that knowing D here, for example, like if you want to like consider the second toss here, you want to predict the outcome of second toss, knowing which dice you're picking, then it doesn't matter like what's your outcome of the first toss already. It doesn't help you in estimate like in predicting the outcome of your second toss as long as you know D already. In other words, like HO2 given like DMO1 should be just equal to HO2 given D because this O1 shouldn't help you in any sense. So therefore, like this is equal to HO2 given D as well. So you just get it cancelled, you will equal to 0. Or actually more straightforwardly, you can say right at the beginning that like because like O1 and O2 are conditionally independent given D, so in this case, this should be just equal to 0. So knowing that since O2, O1, and O2 are conditionally independent given D. So think of like it always say, for me, like I try to think of conditional independence is like uh, more think along the line of this conditional entropy or like the variables that, let's say I have like 3 variables here. This one is essentially like I have a train like this, like O1, MD, and O2, something like that. And I'm thinking like now if I'm going to predict T O2 here with some help of variables, let's say D and O1, if I given D here, will O1 help me or not? If O1 is not going to help me, then I should have a train like this. So in other words, like O1 and O2 should be conditionally independent given the variable in the middle. So is that clear? Um, so if okay, it's not too assuming, I guess. Um, I mean, like you definitely can compute the value precisely. Oh, it's okay. I mean, you can try to compute it, and you will get the same outcome that eventually gets equal to 0 if you compute everything correctly. Uh, but more easily if you see the structure of the problem like right away. You see that like where's the probability coming from? Like I mean, like I uh, consider these two things here, like let's say this one and this one here. Let's see if I can quickly illustrate anything. So so for this one, it will be something like expectation minus log PO2 given DMO1. I'm not sure this writing help a lot. Yeah, but it kind of simplify things a little bit. Okay, yeah, this is the conditional. And know that like you really have like PO2 given A and O1 is just equal to PO2 given A, right? For example. And PO2 given B and O1 is just equal to PO2 given B, right? So because of that, like this one will actually just is essentially the same as like PO2 given D. So therefore, like if you do expectation log minus log of this guy, of course, it's just equal to this conditional entropy like this. So it's kind of like quick and quick way to see that like also like these two conditional entropy should be the same. Yeah. But as I said, like just look at the structure of that variables that you should yeah, you should immediately recognize that that should be some conditional independence somewhere. So okay, I guess what I'm going to do next, I'm going to kind of swap back using my my tab here is a little bit easier to write. And I guess we'll continue what we talked about last time. So we talk about differential entropy, and if we have a conditional random variable, so let's say if x is continuous, okay, continuous. So, and besides, we can still like define entropy as expected minus log px here. So this is the entropy. But note that like this expectation, like because this is continuous, this is a PDF instead of PMF. Then I actually this expectation really is an integral, right? It's equal minus log. It's equal to minus px log px dx, something like that. And we denote this as a small hx here. So it's like the differential entropy. So we also kind of mentioned that we gave an example that, for example, for a uniform distribution for differential entropy, let's say if I have something uniform with this width is A here, this is like the height here is therefore 1 over A here, then the differential entropy is just equal to log A, right? Just equal to log A. And apparently like this one, then it is unbounded. It can be basically, it would be like in the range, it can be negative and positive. It can go all the way like to minus infinity, if like this is like a delta function to plus infinity. And of course, like for if we consider like discrete random variable, we should always have like positive value for the entropy, because like entropy basically means the number of bits needed to store that information, right? So here, like there's no contradiction because like for continuous random variable, it's really have like infinite precision if we think of that. And to connect this to the discrete case, we mentioned last time that like if we do some quantization, and let's say for x have a quantizer here, quantize, if like a quantization step size delta, let's say I call it x delta here. So for example, like my delta is like equal to 0.1, let's say, and I have like this is a input is a pi here 4.1415 something, right? And then like after you quantize, you will just quantize to 5.1, let's say. Sorry, 3.1. And now this I have a discrete value here, right? So I can talk about hx delta. And here I can only consider the differential entropy hx here. So we say we can connect this hx delta if hx is more or less hx delta, we showed it last time. It's just equal to hx minus log delta, I believe. Yeah, let's see, it's minus or plus. Yeah, I think it's minus, right? The smaller the delta, yeah, more bits there. Yeah, so it's something like that. So we gave some example, like for example, for you have like x is a uniform distribution and how many bits. Let me just say go for another example. Let's say example that maybe I have like a group of like 100 students here, 100 students, and then like the height. Let's see, I have the FH height maybe 1.7 meter. Okay, you guys use a okay, you guys use feet, but okay, let me I use metric here. Let's say 1.7 meter, and then like maybe I have a variance. It's like 10 centimeter. Let's say this is a standard deviation. Let's say instead of variance. Let's see, standard deviation is like 10 centimeter. This is the mean. So let's say I store all students height with precision of a centimeter of 1 centimeter. So how many bits are needed? So this is a kind of interesting problem, right? So a reasonable problem. Right? So is that clear what I have? I have like students here. I have like kind of like the student have like some distribution of their height information. Now I want to store all the values of this height information here. Maybe I make it even larger, like 1,000 students here. Now I want to estimate like how many bits are needed like to store all these 1,000 students. Okay, it won't be so fast actually. So you at least you need to visualize two things. First is a number of bits we require will be depends on the precision that you're storing, right? So if you're storing with a high precision, then probably you need more number of bits, right? So that's actually taken into account for by this term here. And also it depends on the distribution itself as well. If the student is more spread out, then more likely you will need more number of bits. For example, if all the students is like precisely like, for example, like you have an extremely small like standard deviation, let's say 0.1, I don't know, somehow you get all group of students have height precisely 1.7 meter. Yeah, I don't know for why you can get that. Then actually most likely you don't even need to store anything because you know that like everyone will be just 1.7 meter. You just need to store a number, right? So or like you almost no need to store anything. So and this is actually taken account for like by the differential entropy here. So I would say like the answer will be equal to this one, but okay, let's try this numerical question here. But of course, like, first of all, like here, I didn't specify the distribution. Okay, let's say this distribution is normal, right? Gaussian normal distribution. I'm actually we will need something for that because we didn't compute the entropy for normal distribution. And for normal distribution, let's say maybe just a a kind of a view for normal distribution. Let's say a normal distribution of x, let's say with parameter mu and variance sigma square, let's say. So um, that it would be have some bell shape here, right? So the mean is mu here, have a more or less a bell shape here is the normal distribution, and then a sigma up about like 3 sigma, you will be, I forgot like how many, cover 95% or something like that, or maybe probably more than that, I forgot. Um, and it's more or less like this. And the PDF, if you remember, I think like most of you may not remember, will be something like exponential x minus mu over 2 sigma square. This is square here. Let it be. Oh, sorry. Like this is just a squid n here. This is normal. Or people like sometimes people call Gaussian. Like, actually, in engineering, people call it Gaussian. In statistics, people call it normal. Normal distribution. Have a bell shape here. And anyone remember the scaling factor here? So it is good at least to remember the exponent here. The exponent is like this. Uh, the the scaling factor here will be something like 2 pi sigma square, I think. So probably I should calculate. Make sure I didn't. Yeah, but I think I'm quite sure I'm correct. But yeah, it's not bad to check. I think I'm right, but I see. Let's see if I have. It's okay. I don't. Okay. Yeah, I'm right. So let's find the differential entropy here. Hx. Let's see. If I'm trying to look for it, it's the bottom squid n and the bottom of the exponent. Oh yeah, sorry for my bad handwriting. Here it says sigma. It's the standard deviation. Square is the variance. 2 sigma square. This is not 6, it's sigma. Yeah, I don't know how to write. Yeah, that's the. Yeah, it's not pretty like 6, but it is sigma. I don't know how I can write more like. Yeah. 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 Okay. So So this is sigma as well. This is sigma as well. This is sigma. Both of them are sigma. So there's the standard deviation. So if you plot out this thing here, you more or less get the bell shape here, and the it will be like at the peak will be the mean here is the mu here is the peak. So more or less the mean is the peak here. I mean decay like quickly and around like 3 sigma. So people call it say 3 sigma, right? 3 sigma, 6 sigma, whatever. Like when you are like 3 sigma where you are the probability getting pretty small. And okay, hx is what? It's just equal to expectation minus log px, right? So remember, like always try to avoid doing calculus first. I see if you can get away doing like any like integration differentiation is okay, but integration, if you can avoid it, like try to avoid that. So see, like this is essential expectation. Of course, I know what I mean is like, of course, I know this is like equal to minus log px, log px dx, and so on, right? But I don't want to do the integral if I can. So let's see. So this one is expectation of this guy. I just substitute this, like this px. I mean, this px is just this n x mu sigma square, right? So it's equal to therefore minus log this thing here. So I will have like log 2 pi sigma square. By the way, like I'm thinking whether I should use lateral log here. Let's use lateral log here for the moment. Remember, the difference here is just the unit, right? I need to scale by. Oh, yeah, it's okay. I guess I'll just keep it. Let's keep it. Log base 2. Let's just do log base 2 anyway. And log base 2 of this guy, I will have plus what? X minus mu. I should write cap here. Be careful. X minus mu square for 2 sigma square and log e here. So it's like this is log base 2. I'm omitting the 2 here. And expectation of this guy, this is a constant, right? It will be just a constant here, log base 2 pi sigma square. And expectation of this, okay, let's look at that. This is interesting. This are just constant, right? I can just pull it out, right? This is like log e 2 sigma square, expectation x minus mu square. Okay, what is this? Like, what is this? Question for this one, what would be this? Can you see that? What would be this? Yes, this is the variance. Very nice. So this is the variance, and so therefore it's equal to should be equal just equal to the sigma square, right? So this is a sigma is the standard deviation, sigma square is the variance, right? So therefore this is actually just equal to sigma square. Wow, super nice. I didn't even do any calculus at all. So I got cancelled, right? So I have like this got cancelled. So I have like log 2 pi sigma square log e plus log e over 2. Oh, I probably missed the, let's see, did I miss the minus sign here? Oh, yeah, sorry, like I have minus sign here, of course. Like, yeah, I'm sorry. I missed the minus sign here. So minus sign cancel, like that's okay. This is plus still, yeah. Yeah. So, thank you for catching that. So, and I have this, and then like, I can group the term here. This is like log a plus log b. Okay, I can, 2 can get into here, like become log e square, right? So wait, sorry, log square with 1/2, let me 1/2, okay. Or let maybe I can write square root here, square e. So log a plus log b is equal log ab, right? So multiply together. So this would be like square root 2 pi e sigma square. So this, so very nice. So note that it does not depend on the mean here. Actually, very reasonable, right? So the amount of information just depend on the shape. So if it's more spread out, that would be more informative. Or like in the sense that you have more information there need to store if you need to store it as the distribution more spread out. If it's therefore like if variance is bigger, then the differential entropy will be bigger. On the other hand, if variance is smaller, then it will be smaller. So now I have this. Okay, I have this here. Can you try to finish this question here? So this question here, how many bits do I need? Do you know? So basically, I know hx now. This is a 1/2 log 2 pi e sigma square, or I write it earlier as log 2 pi e sigma square. So either way is okay. So note that like this is on per sample. I need hx delta bits. I have 1,000 students. I need to multiply by 1,000. Yeah. Hx delta here. Don't forget that again. Let me phrase it again. Don't forget here like hx delta is like per sample on average, how many bits are required to store x delta. So therefore, if I have 1,000 samples here, I need to be like 1,000 multiplied by hx delta. So okay, now you should have all the pieces here. Like, do you know how many bits are required in this case? Okay. Let me try it out myself. Yeah, get a little bit different answer. I don't know whether see. Oh, okay. I mean, like yours probably is too small. Like it shouldn't be that small. Anyone else have different answer? Like I got a different one too. Uh, so I guess I don't know like if there's anyone else here like besides Henry and Sarah. I guess I would just um uh, let's see. So let's see. Should I show the screen again? Let's see. That probably is easier, or maybe not. So, but okay, this one here. Okay, let's just use the formula here. I know the number of bits like per sample will be like so many bits, right? So sigma square. Okay, you can use the unit either meter or centimeter. It's okay. It shouldn't affect your result. So, but in my case, let's use centimeter. So actually use centimeter. It make a little bit easier. Actually, if I use centimeter, you see like this term is actually even gone here. Okay. There's a if I use unit centimeter, then like delta is just equal to 1. My log base 2 delta is just equal to 0. It's gone here. And then like unit centimeter, then like sigma square is what? It's just like 100 centimeters, right? 100 centimeters square. So then hx here is a half log 2 pi e 100. So what do you get? Like this should be like per sample, you should get so many of this. Yeah, you need to square that. So because like that's the variance, not the yeah. This is the standard deviation here. So I think you should get something like per sample. If you substitute that per sample, you should get something like this. I say 5.369, something like this per sample. So I have 1,000 students, so therefore it's 5,369 bits around that order. And you can try it out yourself to see if you, yes, you can try to use meter as well. You should get exactly the same answer. So if you use the unit as meter, then this will be like the variance here will become like 0.001, right? But on the other hand, you have an extra term here. You need to minus log delta. Now the delta is say equal to 0.001. So minus log 0.001, something. So and then you should get exactly the same result as before. Okay, so I've like couple minutes left, And okay, actually, before I don't know, like that's lot. I don't know how many of you guys are actually present, but we have to. I guess we have to do this poll here. Not poll. I sorry, the lottery here, like to design the presentation order. And I guess I will just do it now for the next. It's like 5,300 something. Like per sample, it's like 5.36. But remember that you have 1,000 students here. Each one is 5.36 bits. So therefore, if you store like all 1,000 students, will be 5,000 something number of bits. Yeah. And okay, I'm here. So okay, I'm thinking at least give you 2 weeks time here. So 20 and 27, I'm looking into 20 and 27. So, yeah, that would be like very okay. The problem like it will be like 2 days only. Like um, I guess like half an hour is like something like should be reasonable. So I'm thinking around 5 presentation. One we have like 7, right? So we have 5 presentation for one day and 2 like for the other day, something like 5, 1, 2, 3. Yeah, 4, 5. Yeah, something like yeah. Maybe after the third presentation we have a small break and then have like 2 more presentations, something like. Um, yeah, it depends on the material. I guess some shorter can be like, but I think like half an hour is like reasonable because like otherwise, for example, like I see some of you guys like you talk about packages will be pretty quick, especially like you if you want to go for some demo and so on, like you won't have sufficient time to do that. So to make the talk at least like have some value, I guess I need to around like half an hour. So then I'm thinking like maybe today's is 6, right? So have 5 talks on 6 or like 7 talks on. No, I can do it other way around. Maybe 2 talks on 20, and then yeah, that's tricky. But it's okay. Let's see how. Okay. But I I I create a code, but it's not prepared like that. Let's see if I can. Um, let's see. A second. I guess that would be like 2 guys a little bit unlucky. Would be like have like 2 weeks to prepare. Then maybe like the rest will have like 5. I mean 3 weeks to let's see. Uh Maybe I swap that will work. 27 and 20. So just do one lottery one time. So okay, don't look at that. That's like the previous one here. So 2 fellow is a little bit unlucky. Will be earlier like 20th, and then like the rest will be 27. So I will post a schedule like on the web site, so you should be able to see that. And I will kind of maybe send out a reminder somehow. Like I don't know. Like probably some of you guys are not around. So anyway, like this is a basically the schedule. So yeah, if someone want to swap, like you just this is the time. For example, like Amy, if you want to swap to an earlier day, you can ask Michael. I'm like, Dylan, I guess most likely they would like to swap with you. Like many people like to prepare, like, okay, do it later. So if you want to do it like earlier, I guess it's okay if you want to swap. So okay, that's it. Like I'll see you guys next week. And I may give out homework. I'm still considering that because yeah. So I may post homework, and if I'm going to post homework, you still have like at least 2 weeks to work on that. So I'll see you guys next week then. Yeah.
Well, Professor, before you leave, wanted to ask you.
Yeah, sure. Thank you.
Professor, are you,
Bye now.
Professor, are you